don't even know if I've put up the model answers to the quiz already on YouTube. Could very well be.
We'll have to look.
Could be. Last act. We seem to be stuck at the number 13. Yeah. I know that everybody will come back at one point. It's just interesting that every time I do a hit count, it's 13.
Well, that's not a good sign, is it?
What does that want to tell us?
No, it's 17. It's weird. So they got a massive sample of people around. They found 37 and 73 were both well.
Could be worse.
I just think 37 and 73 are quite fine numbers. So I guess it kind of works out as it's kind of like the most random number.
A random number like
One of them.
I think we've got 16 toilets, right? Yeah. Okay, last act. Hey guys, we get through that, don't we? We can do it if you're being cured. Yes, I'm a sucker for advertising. Okay, last act. I know you are dying to find out what happens to Callum's child. Because right at the beginning, I played a little bit and I asked you to make an educated guess about two samples. Do you remember? Yeah? 1, 2, 3, 4, 5. And the other sample is 3, 4, 5, 6, 7. Because I'm a nice person, I've already given you the sample mean for each sample, X bar, 3 and 5. And the question was, are these two samples in any way different? Is there a difference between sample 1 and sample 2? And you said, what did you say?
Sorry.
What did you say?
I said for yes.
Yes, they are different.
Yeah.
Mm-hmm. Yeah, looks like it, right?
Yeah.
What did we say about the data format?
We weren't sure if it was discrete or continuous.
Aha, you're absolutely right. We were not quite sure whether they are discrete or whether they are continuous, because we don't have any context. And context is, as always, absolutely crucial and important. Tell you what, why don't we just simply calculate and use our knowledge of hypothesis testing? Why don't we use this knowledge and calculate the p-value for both, for continuous data and for data? Do they look like proportions? Yes or yes? No, they don't look like proportions. So what else could they be? Just simply count data, right? Fichy-Poisson data. So why don't we try to calculate the p-values? One for count data and the other one for continuous data, and see, what does that give us? Of course, we would do hypothesis testing. So we would start with a null hypothesis. Null hypothesis for continuous data. Well, we did that yesterday. We said continuous data, there's no difference between the two population means from which the samples were taken. Any differences are due to sampling error. For the count data, we said there are no differences between the two population rates. And any differences that we observe are just simply due to sampling error, and so on and so forth. Right? So these are our data, 1, 2, 3, 4, 5, and 3, 4, 5, 6, 7. Do you want to try it yourself? I would say this part here is doing the Poisson, and this part here is doing the continuous data. Yeah, calculate the p-value. And in order to do that, here is the calculator, because that's exactly what you are probably going to do in the quiz. Yeah. So you are doing Poisson 1, 2, 3, 4, 5, and 3, 4, 5, 6, 7. You are doing the continuous data, the T, two-sample t-test, 1, 2, 3, 4, 5, 3, 4, 5, 6, 7. Yeah, I give you about 5, 6 minutes, and then we do it together. I'll write the data down again. 1, 2, 3, 4, 5, 3, 4, 5, 6, 7. So you do the T and you the count data.
I'll get a good one.
Yeah, yeah. P value. Okay, and then if it's low, then we have to be. Where's continuous?
So for continuous, you want to do the 2-sample t-test on the calculator
I've got
tab.
that far.
Yeah, absolutely. So what you need to do is basically you type in 1,
Yeah.
2, 3, 4, 5
Yeah.
in one, and 1, 2, 3, 4, and 3, 4, 5
Yeah.
in the other. Okay.
I've got my P.
And you've got your P. Let me see your P. Yep.
Okay.
I usually don't ask people for their P.
And then you can reject.
We don't usually ask people for their P's. Yeah. Did you get something? No? Sorry? Good. Yeah, figure it out. That is what it's all about.
We also count occurrences.
You do count. Yes, that's absolutely right. So you add them all up. Yeah.
Add them all up.
You add them all up because you have a total of 1, 2, 3, 4, 5. That gives
Use the mean for an array.
50.
Yeah.
So you add them up.
15, and you have 5 observations, so it would be 15 and 5 in the first row of the calculator. Yeah, but we will discuss that. And the other one is 25, isn't it? So you know how to do that? The T?
Don't we need to do this bit now?
I think that's if you're doing it like manually, right?
What's that?
And so we got this,
Yeah.
and we've failed to reject the.
You fail to reject the null hypothesis.
So we don't need to do this. Calculator
does that.
That was what this. Okay.
That is what this does.
Okay.
It gives you the p value.
Okay.
You don't have to calculate the t value.
Okay.
Yeah, because the t value calculation is not what I showed you, because we use this Welch test.
Okay.
All right.
Yeah, so you just go for the p value. Yeah. Okay, have we got some results?
How do you work out the number of days?
Okay, I'll go through that. Yeah, shall we do it together? It's you're absolutely right. It's 5 observations.
Yeah, is that done per day?
Yes.
So the mean is the days. Okay, so.
No. What? The mean? No, you just calculate what is the average.
Yeah,
To take that. 5, 3, and 5.
What's the mean
Yeah. Yeah. You still can calculate it.
Oh, right.
You still can calculate the mean.
So the day is not just one.
No. Okay, so. Okay, most people have sort of done it. Let's do the calculations. So let's start with the Poisson first, because you are on that side. So what we need to do is we actually look at each sample. Of course, we can calculate a mean and or the average, and this is exactly done like any other average or mean. We just add them all up and divide by the number of observations. So the first one, 1, 2, 3, 4, 5, added up gives us 15, right? And the average, we have 5 observations. 15 divided by 5 equals 3. That is what I've got there. For sample 2, we've got 3, 4, 5, 6, 7. According to my calculation, this gives 25. Is that right? Divided by 5 is 5. So the mean is 5. Good. So how do we do that? In the calculator, we say it is count data. It's not a proportion. We treat that, for the time being, because you're on that side, we treat that as discrete data. So let's go to the calculator. And for the first sample, I have a total of 15 events, yeah, all added up. And it was 5 observations that I have. And it would give me the confidence interval, the 95% confidence interval from 1.7 to 4.9 counts. If somebody should ever ask you for the confidence interval. Could easily happen, couldn't it, in a quiz or so? Okay. And we do the same for the second sample, 25, and again 5. We get the confidence interval here, 3.2 to 7.0. What we are interested in is the p-value. And of course, this gives us the p-value. And the p-value is 0.15. Yeah? Did you get that when you tried to do that? Yeah, 0.15. Okay. Reject or fail to reject? You are the expert?
You fail to reject.
We fail to reject the null hypothesis and say p-value equals 0.15. Brilliant. So there is no difference between the two samples, treatment or placebo, if we treat the data like count data in the Poisson distribution. Yeah? Okay. So now let's deal with you lot and say, but what if the data is actually continuous? How do we deal with that? So we go to two sample t-test and we enter the data. So we have 1, 2, 3, 4, and 5. And here we enter 3, 4, 5, 6, 7. Okay. So it's always a good idea to check here in this gray area where you're just about to see it. Actually, I can click on that. So the mean is 3, yeah, and the count is 5, and the standard, the estimated population standard deviation, estimated, is 1.58. Okay, that's good. And here we can do the same. Just make sure that you check what you enter. Very important for clinical trials, that you always check that you haven't missed anything. And here we've got also 5 and 5. We've got the same variance, so that's or standard deviation, which is nice, good. We can deal with that. We see the 95% margin of error for each. Okay, that's this value here. And when we look at the confidence intervals, the confidence interval is given here for the first sample between 1.037 and 4.96, or for sample 2 between 3.037 and 6.963. That gives us the lower and the upper bound of the confidence interval. And now the crucial moment, our p-value equals 0.08. Yeah, that is where you find the p-value. That is what this calculator gives you. So we've got the p-values. So Poisson, we said this was 0.15, and t-test, we got the p-value of 0.08. And here we said we reject the null hypothesis. No, sorry. We didn't say that. We didn't say that. What did we say? We fail to reject. What about the t-test, the p-value? Fail to reject the null hypothesis. So that's why you're childless. Yeah. Don't worry. Don't worry. Don't worry. Right? Don't worry. Don't cry.
Right, me too, don't worry.
Count yourself lucky.
I lost mine in a biostats.
Count yourself lucky. The monsters just bleed you dry. Give me dogs. Yeah, dogs good. Children. My children actually think that I love the dogs more than I love them. They said that.
Is it true? Yeah.
What a question. Of course it is true. Yeah? The children.
Yeah, they should do.
Maybe you love them as much.
Well, if you say so. Okay, so you said they are different. The p-values tell us they are not. I'm very sorry, right? So far, so good. So there's no difference between them. However, there's a slight however. If you stop here and go home, brilliant. But if you want to get even higher marks with your employer, not for the assessment, because I haven't included that in the assessment, but if you want to get to the bottom of things, you also calculate the effect size. And we haven't discussed how to calculate an effect size for Poisson data. It's a slightly different story. But I showed you how we can calculate Cohen's d for the continuous data. And Cohen's d, when you do this calculation, or on my website, there is also a calculator under advanced calculators, a common effect sizes. When you do that, you get an effect size of 1.1. Now, of course, you need to rewind and say, what the hell does 1.1 actually tell us in terms of effect sizes? Let's see if I can find it when we did that. think we did that. Yes, did we do that yesterday? I think so. Comparing proportions. Good Lord, we've done a lot, huh? Day 3. Sorry? Before, aha! Here it is, effect size. We have an effect size Cohen-D of 1.1. What does that mean? It is larger than large. Yeah. So our Cohen's D is large. There is a large effect, a large difference between the two samples. So you were right. Yeah? Don't worry about your baby. Still, you know, it's still, you don't have to, you haven't sold it to the devil. I.e. me. But you see the problem. Our p-values tell us there's no difference. Cohen's D tells us not only that there is a difference, it tells us there's a massive difference. There's a bit of a tension here, right? Who is lying? Somebody must be lying, because we can't come to the same to totally different conclusions with the same data. P-value says no difference. Sorry?
That's called marketing.
That's called marketing. Yes, that's true. P-value tells us no difference. Effect size tells us massive difference. Where's the problem? What could it be? Stats doesn't make sense. We haven't done anything wrong. We actually haven't done any complicated calculations because we let the calculator do all the calculations. So we just did some comparisons. And okay, you have to take my word for it that Cohen's D is 1.1. Actually, I had to add a little bit of a correction factor, but let's not worry too much about it. Okay, stats doesn't make sense. Well, it could very well be the case that the assumptions of the t-test are not 100% met. Even for this Welch test that we are using, could very well be that they are not met. Now, for the Welch test, we said we don't need to worry about the sample size. Well, we have the same sample size, so that's not a problem. We don't have to worry about the same variance or same standard deviation. So it doesn't really matter because we've got the same standard deviation. So that's not a problem. But another thing is maybe the data are not independent. Well, actually, they are pretty much independent because I just made them up. The last one is they might not come from a normal distributed population. That could be very well the case because we've got only 5 data points and they are all different. So it would be very difficult to say, do they come from a normal distributed population? So that could be one issue that we are dealing with. But another issue is actually we have only 5 data points, right? And 5 data points, the big question is Is that enough? 5 data points. Why don't we do clinical trials with just 5 patients? It would be so much nicer in terms of recruitment.
I'd get you the perfect patients.
Yeah? Would be so much easier. Why don't we do that? Well, actually, the p-value depends on the sample size. Very much so. I showed you yesterday with the Poisson distribution and the proportions, the p-value really depends on sample sizes. The effect size does not depend on the sample size. So what is the right sample size that we need? And that is actually a very important thing to ask, because in a clinical trial, if we don't have enough patients, is that a good thing?
You don't have patients. No.
If we don't have enough patients, you know, we can't really say anything. If we have too many patients, is that a good thing?
No. Well, it depends which way you look at it. From a stats point, probably, but from an ethics point, no.
From an ethics point, no. From a cost point,
No.
absolutely not. So you want to have sort of the Goldilocks patients, right number of patients. So how do we find the right number of patients? Well, the right number of patients that we find actually has something to do with this. Where am I? The right number of patients has something to do with our conviction table. So remember, we asked, did Hope commit the crime? Yes or no? And do we make the conviction? Yes or no? And we said we have 4 options. We said, if we convict her, although she didn't do it, it's a type 1 error. If we don't convict her, but she did do it, she is laughing and still eating my chocolates, we have a type 2 error. Now the question is, do we have enough evidence if she did it? So what we are looking for is exactly this one here. We want to make exactly the right decision. We need to make a guilty verdict if indeed she did it. This is also called a true positive. This one here, of course, would be a true negative. So we want to know, how much do we need? How often do we actually find true positives? How often do we make the right decision if the person is guilty? And we want to sort of keep that as high as possible. But if we are too strict, then on the other hand, we would probably increase our type 1 error. We would make too many convictions if they are not guilty. So this one here, this area here that I circled, that made bold, this is actually calculated by 1 minus beta. So we've got beta and 1 minus beta, and it has a name. One minus beta is referred to as the power of the test equals 1 minus beta. 1 minus the type 2 error that we have. Now, of course, there's a sort of a trade-off between alpha and beta, as I said. If we want to make as many convictions as possible that are correct, we would reduce alpha. If we are more lenient, we increase alpha. If we reduce alpha, if we are very, very strict, we would get cases who did it, but who get off without any sentencing. And like alpha, you can usually set beta at liberty, and a very common value is a little bit like the 0.05 or the 5% significance level. Very often beta is set to 0.2 or 20%. What does that mean? It means in 20% of the cases, we commit a type 2 error. Type 2 error. That means we would not claim that the person did it, although they did it. Type 2 error would be, we would say the drug has no effect, although it actually has an effect. Now, if you are a drug discovery company, this is a big thing for you, because if you say the drug doesn't have any effect and it has an effect, you would potentially miss out on big business. You could find a drug that, brings hair growth back. Would be a massive business. But you say, well, the drug doesn't do it, bin it. Your competitor brings the drug on the market, and you kick yourself. So what you want is really a sort of a balance with beta around 20%. And what you want is a test that has a power of at least 80%. A power of 80% means in 80% of the cases, you make the right decision in saying, yes, the drug has an effect when the drug has indeed an effect. That is what is power. That is true power, if you think about that. Now, how do you calculate that power? And also, what does this power depend on? Let's try to use our intuition a little bit. And we say, we know that sample size is crucial. And the power also depends on how big the difference actually is, how big the effect size is. If you've got a massive effect size between placebo and drug, for example, it's easy to spot that there is a big difference, right? So I probably don't need a lot of samples for that. But if the effect size becomes smaller, if the difference between the two samples becomes smaller, I need a sort of almost a magnifying glass. Ooh, is there something? A magnifying glass in this case means we need a higher sample size. So what we can actually do is, and I think I've got, yes, I've got a nice graph for Cohen's d. This graph actually shows you the statistical power versus the sample size for each group that we need. And if we want to have 80% power, so we want to be really sure that we've got the right decision, that we say, yes, the drug actually has an effect, when it does, then we can see with this dashed line here where this comes down, how many samples we need. And it depends on Cohen's d, on the effect size. So here we've got the effect size of 0.5. 0.5 is a medium-size effect size. Now, there is actually an equation that we can use. And very roughly, if you've got alpha of 0.05 and the type 2 error of 0.2, then you can roughly estimate the sample size that you need by the equation required sample size equals, and it's about 16 divided by the square of Cohen's d. The 16 comes from a number of factors, including alpha and beta and things like that. It's just simply easier to remember as a sort of, 16. So let's calculate what our sample size would be or what sample size we need actually for a Cohen's d of, what did we have? What did we say? It was, where's it gone? Have I missed it? Have I lost it? Not. We said Cohen's d was 1.1. Yeah. So let's calculate what sample size we actually need if we want to see 1.1 or larger. So 16 divided by 1.1 squared equals 13. What does that 13 mean? So in order to see an effect size of 1.1, we need to have 13 observations per group. only if we've got 13 observations per group or more, then we would be able to detect reliably something with this effect size. Did we have 13 per group? How many did we have? 5. So we did not have enough observations to reliably detect even a large effect. With 5, with sample size of 5, we cannot detect reliably, true positives, even if the effect is large. Even effect size equals large. In statistics, you will find that very often that people say that our test was underpowered. Test is underpowered. Does not have enough power even to detect a large sample size. You can now say, for example, what would be the sample size if the effect is small, if it's medium? Yeah. Very often we don't work with large effect sizes. It doesn't happen very often that you are so lucky to see a massive effect size, a massive difference. Very often you see more subtle differences. Yeah? So we can ask, how much patience do we need if we just simply have a smaller effect size? And here you can look at that. So for a much smaller effect size of 0.5, you need far more patience. You can actually calculate that. If we have d equals 0.5, let's calculate that. How many patients do we need? 16 divided by 0.5 squared equals 64. So per group, we need at least 64 participants for each group to detect a medium size difference. And very often in drug trials, you have much smaller effect sizes, 0.2 or something like that. Still worth pursuing, bless you, but you need large numbers. Otherwise, your test is underpowered, and you would not be able to see an effect even if there was one. So, when you said you believed that there is an effect, the p-value said, no, there isn't. Cohen's d said, yes, there is. We probably have to say the tests that we used were not suitable. The test was underpowered because we only had 5 observations per group. And therefore, we can't really come to a conclusion everything is safe. It could be that it could very well be that there is a big difference, what Cohen D says, but the tests that we used just simply would not be able to pick that up. Yeah? So intuition was probably right. Thank God for that, hey? Yeah, that's, you know, we leave it like that. We leave it like that for the time being. So that is a power analysis, and every sort of statistical analysis that you should do should actually contain a power analysis to critique, have I done the right thing? Have I used the right test? And it also means, yes, we need to look at the assumptions. So what I'm going to do now is yet another short break. And in the last session, I will tell you how we can overcome this issue with assumptions. Okay, I know it's long, and hopefully it won't take too long for that, so that you can go. Do you have a session afterward? Yes. Kirsty. Good. So yes, but I will try to finish by past. Yeah? Okay, back in 7-8 minutes. Okay?
Nearly there.
Nearly there.
I'll go downstairs because it gets
That's not really,
And he goes,
so I had
What every person views.
and it's just about, you know, it's such a such team. Oh, right, they want to stop shooting. I was saying, oh, okay. I was saying to work as it was like that. Can you stop when you say something? They're like, no. wait until your masters at least. I was going to tell you quickly. Yeah.
Sorry, Peter. If you don't know like what test to use, like does it tell you in the question? Like, you know, you're saying context clues, or is this what you're going to explain?
the test.
Yeah.
The quiz.
Well, oh really? Oh, okay.
So, for example, when it says assume the data are Poisson distributed,
Okay.
it's a bit of a giveaway.
Yeah.
If you see some continuous data, for example, with decimal points, and it's not the same number in the two columns. Sorry?
What do you mean not the same number? Like,
So,
like different?
we talked yesterday about the dependent or matched t-test, yeah? If you remember. And each
You said there's like 10 here.
10 here and 10 there, yes? That could be a matched test, or it could be an independent test. But if the numbers are different, so 8 and 10,
Yeah.
you know it can't be a matched test.
Yeah.
It would be just simply a two-sample t-test.
Okay.
Yeah? Does that make sense?
Yeah.
And if it is a sort of a proportion or something like that, you probably figure that out as well. Please don't stress too much about the quiz. I personally think that it's probably an insult to your intelligence. So, and if you score less than 80%, I will be most seriously be pissed off. Yes. And I'm recording that.
Yeah. Oh, yeah, it's on my phone, it's on the recorder, isn't it? Oh, I'm gonna go.
Once I use the F word in a lecture.
Oh, yeah. I'd get sacked. Oh well, it's not like I'm being paid.
Well, actually, it wasn't recorded. And I denied all knowledge. I said probably it was fake. Which is, you know,
German word.
Irish.
Or like they close the door just in time when someone comes up.
Uh-huh. Cute.
So, yeah. Possibly.
Your Honour.
It was not me. Nobody saw me. And I have a free fall.
Yeah, I'm going home quite early.
The trip hazard's a bit higher now, really step over there.
I need to check, actually. Aha. Aha. Ah. Okay. Mm-hmm.
Are there other portfolios?
So what do you have to do for this module? I was told this is a module, right?
Yeah.
You have to do the quiz
And the quiz and the portfolio.
and the portfolio.
Yeah.
What's in the portfolio? What do you have to
There's like 5 questions The first one, actually, no, the quiz is part of the portfolio. Sorry.
Aha.
So there's a quiz. We also have to do an organogram from our company, like in terms of the stats department. What else do we have to do? We have to do the simulation thing. There's like a bunch of questions basically that we have to do for the portfolio. And it's
750-word essay.
Sorry?
And it's 750 words.
750 words, that's 1.5 pages.
Well, if you don't, yeah, tables are right there.
And ChatGPT?
Just go over that. We both know that. Did you enjoy your
So have we got most people back? Okay.
Can you behave?
Okay. Yeah.
Teach the remaining part of the lesson with that down.
Yes,
With what?
I've been wanting to see them flipped down since I saw them. I love it.
For half an hour, you're going to teach like that.
I'll try. I'll
Try?
try. No, I can tell you what the story behind that is, right? It is in October last year. I had a cataract operation.
Oh, right, okay.
And it went wrong.
Oh no.
And what it did is it made me very sensitive to glare.
Right.
And they still don't know exactly what's wrong. So I've got tests, I've got MRIs and things like that. And occasionally, when the lighting is not good or something like that, it's glare and I can't see. I'm basically blind. I would walk into a lamppost.
Right.
That's with that, I can, adjust it.
Yeah.
And I can see. On the downside, it's darker and I can't see. So that's why here the lighting is all right most of the time for me, but if it gets too tricky, then I put it down. Right. But if you want this, I'm perfectly happy to comply.
Did you make it yourself?
Sorry?
Did you make that yourself?
Oh no, you can buy it. Oh yeah, you can buy it in different shades and different colors.
Does it just clip on, or is it like part of the glasses and stuff? Yes, that's very good. I like that. I like that.
And especially when you are, for example, when you're driving at night, and you have and glare is an issue when it's raining or something like that, and cars are incoming, glare is an issue. You can get these glare filters. You just put them on and job done. So.
Well, thank you. I've learned something.
Yes. Different from stats. Yeah. Right. Let's get this done as quickly as possible. What I want to say. Okay. P-values can lie. And also, we said a big issue is the assumptions of tests. So t-test, we need to be careful that the assumptions are met. Main issue with t-test is normal distribution, that the population are normal distributed. And usually, or very often they are, but with small sample sizes, it can be get a little bit murky. And any test that is based on the parameters of a normal distribution is actually called a parametric test. You probably come across this phrase. A parametric test is based on, well, we assume that the population is normal. And then there are, of course, non-parametric tests where we don't have this strict sticking to a normal distribution of the population. So, for example, chi-square tests and Poisson test or proportion tests, they are not parametric because they don't rely on the normal distribution. Normal distribution only holds true for continuous data, so discrete data would not make any sense to be parametric anyway. So I just want to introduce the difference between parametric and non-parametric tests. Now, what do you need to do if, for example, your samples are not normal or appear not to be normal distributed? I told you we can do a log transformation where you just simply take the logarithm of each value of each observation, and then it usually or very often becomes more normal. And then you can do your t-test on this transformed. If it still doesn't work, well, there are other tests that you can use. So for example, a parametric test would be a t-test. That would be t-test. If with the best will in the world, you cannot make any changes so that the samples appear to look from a normal distribution, you would use a non-parametric test. And the non-parametric equivalent of a t-test is something that is called a Mann-Whitney U-test. Yeah, you've done that in psychology, didn't you? Mann-Whitney U-test, where you actually do not compare the samples, but you compare the ranks of the samples with each other. So you rank the samples from smallest to largest, combine ranks and do weird stuff, but you would usually use some software with that. But it will also give you a p-value. Non-parametric tests usually have less power than parametric tests. It's just a quirk of non-parametric tests. So whenever you have the option of going for either parametric or non-parametric, go for parametric test because it has higher power. That means your sample sizes can be a little bit lower. But if you can't, then there is always a sort of another test that allows you to do things in a non-parametric way. And as I said, there are loads and loads and loads of tests. Here's just a small selection of what your population could look like. Most of the time, we are working with this one here, with the normal distribution and the t-distribution. These are the most common ones, but the others do exist. And each one of these distributions has a parametric and a non-parametric test, or at least has something. I shouldn't say not parametric or non-parametric. That was wrong. For each of these other distributions, you can come up with a test where you say, if my population looks like that, then I need to use this and this and this test. And I can get slightly overwhelming, especially at the beginning when you do at the start of biostatistics or something like that. What test do I actually need? Now, I was asked in the break, how would we know which test we should use for the quiz? Hopefully, it will not cause too much of a problem, because if it says, for example, assume the data are Poisson distributed, you know what to do, right? Count data, Poisson distribution. Says on the tin. If your data look like continuous data, so with decimals or something like that, or the context is it's decimal, and you have different numbers of observations, then you can be pretty sure that you probably need to do a two-sample independent t-test, yeah, because the data are then independent. For a dependent t-test, you would always have the same number of observations, because you've got patient 1 with 2 measurements, patient 2 with 2 measurements, and things like that, like we did yesterday. But if they are different size, then it's probably a t-test with different independent samples, yeah, something like that. If it is a proportion, if you are asked for a proportion, well, again, you would use on the calculator the tab that we used for the proportions, the chi-squared, yeah, that we did. I promise you, the test does not contain any sort of weird and wonderful stuff that we haven't covered. So everything that the test will ask has been done in these sessions. And it will be, again, it will be on this website. Where's my website? My website disappeared. Yeah, here is the website, the QR code, but you probably have that. So please make use of that. And here's the calculator again. And you are strongly advised to use the calculator wherever possible. Yeah. There are, I think, I have absolutely no idea how Kirsty set it up, but there are 3 questions which potentially ask for different areas of what we have done. So it could be, for example, I just make something up. The first question could be about continuous data. What test would you use to analyze that? Maybe find the margin of error or calculate the lower and upper bound of the first and the second sample and things like that. And you just simply can put that, it's a noodle quiz. The second question could be find the estimated population parameters. So bear in mind, we made the difference between the observed mean and standard deviation, and where we estimated things by, and where you had to divide by n-1. So there is a difference. Yeah? And you need to figure out which one is used. And there could also be a question of proportions, or there could be the topic of Poisson distributed counts. Yeah. Do not stress about the test. With the calculator, you can easily do it in 10 minutes. You've got 3 hours, I think. Come on, come on. If, I was saying that earlier, if you don't all score at least 80%, I would be seriously pissed off. All right? Mm-hmm. Okay, nevertheless, I told you we've got all these tests, all this horrible stuff. Wouldn't it be nice if we could sort of come up with some shortcuts. Which test do I need to use, and so on and so forth. And lo and behold, there are some shortcuts. But the downside is, for these shortcuts, you use a slightly different statistical approach. And this approach, to my knowledge, has not yet been or has not been fully approved by regulators. This approach is called a computational approach. But I personally think this is absolutely fantastic, because in most cases, it doesn't matter whether the data are continuous or count. You get the same, you can use exactly the same thing for everything. This computational approach doesn't care whether it comes from a normal distribution or not. It does the job for you. How does it work? Okay, our data set. 1, 2, 3, 4, 5. I just had to do it, right? That would be our normal data set, with which we have done all the statistics. The computational approach says, I want you, let's do it here. Let's pretend we do a computational approach. Your task is pick one number from this sample. Say it.
3.
3. Okay. Your task is the same. Pick one number. 4. You can use the same numbers.
3.
3.
1.
5. Excellent. In the computational approach, you take your numbers that you have from your sample and randomly choose the same sample number. Okay, pick one number. 2. 4. 4. 5. 3. And what we do is we calculate the sample mean of our original data. We calculate the sample mean of this one. We calculate the sample mean of this one. And you don't do that 3 times. You actually do that 10,000 times. Yeah? Just randomly, with repeat, select the numbers from your original sample. And then you take these numbers and calculate what Colin previously suggested. You calculate the mean of all these 10,000 that you have taken. And this mean will be very close to the true population mean. Yeah? The downside is you have to do that 10,000 times. But if you have a computer program, for example, that loops through it and says, I pick 10,000 times a random number, then it's absolutely no problem. And I can actually get a sort of a distribution of this means. So I plot here the individual sample means that I've calculated, And what you find is when you plot that, it does not matter what your population initially looked like, whether it was discrete data or whether it was continuous data, it will always end up with a normal distribution. Ideally, you want to pick more than 5, but if your initial sample size is only 5, all the other sample sizes have to be 5 as well. But if it gets, if the numbers of observation gets bigger, then the curve gets much smoother. Sometimes if you have only 5 or 6 observations, it's a little bit jaggedy, but it will always default back to a normal distribution. And with a normal distribution, all we need to do is we can say, yes, we want to find a 95% confidence interval of our sample, for example. So all we need to do is take this normal distribution and say, where in these loads and in the sea of 10,000 means, where are the 95% of the data? So the computer does that all for you. As I said, that is why it's called computational analysis. And the method that we use for that is actually has a name. It's called bootstrapping. There is a slight caveat in that, because when you just simply take the 5 numbers of your sample, you will always get the same mean, of course. But if you let the computer do it 10,000 times, there will be 10,000 means. Yeah. So, and these means will be different from each other. Sampling error. So what you basically do is you create more samples with sampling error built in. And as a consequence, you will probably not end up with the same population mean all the time. So if you do that 10,000 times, you get a population mean, mu1. If you do it another 10,000 times, you get another population mean, but it might be slightly different. But you still can use that for basically these tests. In this case, you would just simply test, are these 2 means the same? With the confidence intervals then. And you sometimes get slightly different p-values because you have introduced an added level of randomness. But if you do that frequently enough, then you don't have to worry about which test to use, because the computer will do everything for you. And that is the beauty of this computational analysis. On my website, there is also a calculator that does all the calculations with this bootstrapping method. And you can play around and see, are there any differences between the traditional tests and the sort of the bootstrapping method, the computational method. So that is a little bit more, you need a computer for that, because 10,000 times calculating the mean, you go totally gaga. You don't want that. But it is a very nice way of dealing with things and not have to worry about assumptions. Is it normal distributed or not? Now, we said that the p-value gives us an indicator, but as we discovered earlier, the p-value can be misleading, especially when our samples or when our test is underpowered. And therefore, people sought the p-value. There's a sort of almost a renegade movement amongst the statisticians who say p-values, that is so last millennium, couldn't we come up with something better? Because at the end of the day, what a p-value does is it just gives you a decision about the null hypothesis. We reject it or we fail to reject it. But it doesn't say anything about the alternative hypothesis. And in a way, it's also not very intuitive. Everything that we do here is not intuitive. That's why statistics is hated by so many people. Take the confidence interval, 95% confidence interval. When you ask people what does a 95% confidence interval tell you, the correct answer is, and you will be surprised, the correct answer is it tells us where we should think the true population mean should be. That is as far as it goes. A lot of people say, oh, I'm 95% sure that the confidence interval, that the true population mean is included. No, it doesn't mean that. Or 95% of the times, the true population mean is included in this confidence interval. Now, either the true mean is included or not, but not 95%. You can't give birth to a 95% of a person. Not possible, right? The true meaning, the true definition of a confidence interval actually is if I took 100 samples from the data, from the population, I can calculate 100 confidence intervals. And I showed you how we can calculate these confidence intervals. But if I took 100 samples, I would get something like that. And in 95% of these 100 samples, there would be my true population. It's a totally non-intuitive definition, but it has been sort of accepted by statisticians and by people in general. Oh yes, 95% confidence interval, it tells us where the true population mean roughly should be. But otherwise you can't say anything. And therefore, this renegade group of statisticians, they said, this is all sort of esoteric bullshit. It doesn't make sense. It's not intuitive. Can't we come up with something different? Can we come up with a statistical approach that makes far more sense to people? And the answer is yes, there is something that makes far more sense, but it is not taught in schools, this approach, although it makes far more sense. It is used in clinical trials because this approach, it's called the Bayesian Bayesian statistics. That's why Bayesian statistics. It was actually developed 200 years ago, over 200 years ago, by a pastor, actually, who came up with this idea. And it says p-values we don't know. We have no idea what p-values are. Bayesian statistics doesn't work with p-values. But how does it make decisions? Well, if I come back to our delinquent, it basically says, okay, we need to make a decision. Did she do it or not? And did she steal the chocolate? And unlike the approach that we discussed before in the last three and a half days, which is called the frequentist approach, we say, well, we have an inkling already. The Bayesian approach works with prior knowledge. It works with initial assumptions. Initial assumptions, which is called prior knowledge. So in our case, give you an example. My prior knowledge is, I don't trust girls. Very clearly she is female, so yeah, I got a sort of almost a prejudice in the first place, yeah? Okay, that is my prior assumption. Now I gather evidence. And you tell me how this would sway your decision to make her, to send her down to prison or not. So, I don't trust her. I don't trust her. I found some chocolate wrapper in her bag. How does that change our assumption about her? Guilty? Does it make her feel more, does it make her more guilty in our eyes? Yes. So what we've done is we updated our prior assumption with the data. We came to a new conclusion. Yes, it makes her. Okay, next observation is she is allergic to chocolate. What's your conclusion? Does it make her feel, does it make her more guilty?
Yeah.
Yes, if she's allergic to chocolate.
No.
No.
What if they just like stealing?
It's not.
That for it. It's a
So the updated version is, oh, wait a moment. She's allergic, so why would she eat chocolate? Right? Less guilty. She's got a little brother who absolutely loves chocolate. More guilty? Less guilty? More guilty. The brother is also allergic to chocolate. Less guilty? More guilty?
The brother is allergic to chocolate but likes chocolate.
No. She has a brother. Yeah. Did I say he likes chocolate?
Yeah.
Oh, okay, good. Okay. That was a red herring. So she has a brother, little brother, right, who might like chocolate. But brother is also allergic to chocolate. Makes it more guilty or less guilty? Less guilty. So what Bayesian statistics does is it says we are going in with a prior belief and constantly update it until we've exhausted all the data. At the end, that is what we stick with. And in a way, it makes sense. Yes? The way it does that is mathematically rather complex, and I think that is why it's not taught in schools, because you actually need a good understanding of how you manipulate equations, how you actually differentiate and integrate functions, because that is what it's constantly doing. It gives a sort of a probability. When I say, at the end, we are not working with p-values, we are working actually with a probability. It is fairly likely that she didn't do it. But it doesn't give a defined p-value. It gives a sort of, yes, it's between 20 and 50%, I'm sure that she didn't do it. It doesn't say that, it gives you basically a range. And this Bayesian statistics is becoming more and more interesting for people because they realize that p-values might not necessarily tell you the whole story. So if you've ever come across something like Bayesian statistics, there are lots of YouTube videos and things like that out there. Have a look at it. It's dead interesting, as long as you don't have to go into the full-blown maths. Any questions? If you do have any questions, or if there's something not clear, check out the website, and please do feel free to contact me. Say, "Oi, Peter, not a clue what you were talking about," or "I have this problem. Do you mind looking at it?" And I'll be more than happy to usually help if I have time. Any further last comments? Yes.
Is there anywhere that has like similar, just sort of like a practice question to the ones that will come up in the test? Because I feel like I've learned things, but I haven't had the chance to actually like try it out. Like
You'll be able to. There'll be many exam papers on.
Okay. Okay. Right. Let's see if I can answer this question. If you absolutely insist. If you absolutely insist. I have a website with unlimited practice questions where you go to analyzing data. And I will put up the link to this practice calculation website on the other website if you want. Yeah?
Yes, that would be great. Thank you.
Any further comments, questions? Thank you very much. You were absolutely fantastic. I really enjoyed working with you. And I wish you all the very best. And be good. Don't do anything I wouldn't do. And enjoy your apprenticeship. Take care. Bye-bye. Thank you. Thank you.